All right, let's just jump right in. Have you ever stopped to think about how the solid, predictable world you see around you, I mean, the chair you're sitting on, the air you're breathing, is actually made up of literally trillions upon trillions of frantic, jiggling, invisible atoms? It's a huge puzzle. So today, we're going to build the bridge that connects those two completely different worlds. That bridge is called statistical mechanics.
This is the big question, right? Down at the microscopic level, you have utter chaos, particles buzzing around, bouncing off each other randomly. But up here, in our macroscopic world, things follow nice, predictable rules. Hot things cool down, ice melts. So how does that stable order emerge from all that underlying chaos?
And when we say trillions, that's not even scratching the surface. The sheer scale of the problem is just mind-boggling. In a single glass of water, you're looking at a number of particles with 23 zeros after it. There's no computer on this planet, or any we can even imagine, that could possibly track every single one of those particles. So trying to follow each one, that's a complete non-starter. We need a totally different way to think about this.
And this is our solution. Statistical mechanics is the brilliant idea that lets us understand the whole crowd without needing to know what every single individual particle is doing. It uses the power of statistics, of averages and probabilities, to predict the group's behavior. It's the tool that builds that bridge from the microscopic molecular world up to the world that we can actually see and feel. So to build this bridge, we're going to need three big, sturdy pillars. The very first one is built from the oldest, most familiar set of rules we have for how the world works. Good old classical mechanics.
You know, this is the world of Isaac Newton. F equals ma. It's a beautiful clockwork universe. If you know exactly where a planet is and exactly how fast it's moving, you can predict its entire orbit, perfectly for centuries. It's precise, it's deterministic, and for big stuff, it works incredibly well.
But here's the thing, here's the catch. When you try to apply these same neat, predictable rules down to the level of a single atom or an electron, they just fall apart. They don't work anymore. It turns out the universe, at its most fundamental level, is playing a much, much stranger game.
Which brings us to pillar number 2, and this is where things get really weird and frankly, a lot more interesting. We have to talk about the strange but true rules of quantum mechanics.
And this slide really gets to the core of it. It's a complete shift in thinking. See, classical physics says the particle is right here. It's a statement of fact. Quantum mechanics says, well, there's a pretty good chance it's here and a smaller chance it's over there. It completely throws out certainty and replaces it with probability.
Now this is the legendary equation that runs that whole world of probabilities. And don't worry, we are not going to try and solve it. But all you need to know is that its entire purpose in life is to calculate something called a wave function. And you can think of that wave function as basically a probability map for a particle. It tells you the odds of finding it in any given state.
Quantum mechanics also gives us this other super important idea, and it has a kind of weird name, degeneracy. Now, it sounds complicated, but the idea itself is actually pretty simple. All it means is that you can have a bunch of totally different microscopic arrangements of particles that, when you add it all up, have the exact same total energy.
And this dice analogy is just the perfect way to picture it. Let's say the total energy of your system is like rolling a 7. Well, there are a whole bunch of different ways to do that, right? A 1 and a 6, a 2 and a 5, a 3 and a 4, those are all different degenerate states. But what if you want to roll a 2? Well, there's only one way, a 1 and a 1. And here's the key takeaway. Systems in nature are way more likely to be in a state, like 7, that has more ways it can be made. That's a huge piece of the puzzle.
Okay, so pillar 1, the classical rules. Pillar 2, the weird quantum rules. Now for our third and final pillar, we need the laws that describe the big picture, macroscopic world that we're trying to explain in the first place, the world of thermodynamics. These laws are the undisputed champions of large-scale physics. They describe everything from car engines to the entire universe. The first law is simple. You can't create or destroy energy. But that second law, that's the one that's really profound for our story. It basically says that things, if you just leave them alone, tend to get more disordered, more messy over time. And that measurement of messiness has a name, entropy. It's why your hot coffee always gets cold and never spontaneously heats up. It's why cream mixes into coffee, but you will never ever see it unmix itself. This tendency towards increasing entropy is a fundamental rule of our world. The thing is, thermodynamics tells us that it happens, but it doesn't really tell us why. And physicists have developed some really clever mathematical tools to handle these thermodynamic problems. Sometimes it's just easier to describe a system using its temperature and pressure instead of, say, its total energy and volume. Think of it like describing a circle by its radius instead of listing every single point on its edge. It's just about choosing the simplest perspective for the job.
So, let's take stock. We've got our 3 pillars. We have the original classical rules, we have the true quantum rules, and we have the observed large-scale laws of thermodynamics. Now, finally, we can see how statistical mechanics connects all 3 and actually builds the bridge to reality. So let's just lay it all out one more time. Classical mechanics gave us that initial language for motion and energy, but then quantum mechanics came along and gave us the real rules for the atomic world, the world of probability, and crucially, those degenerate states. And all the while, thermodynamics was there describing the world we actually see and measure, giving us concepts like temperature and pressure. And this is the grand finale. This is where it all clicks into place. Statistical mechanics connects everything by simply applying the laws of statistics to all of those countless possible quantum states. It shows us that the laws of thermodynamics, like entropy always increasing, aren't some deep, mysterious commands. They're just the most probable outcome. Your coffee cools down for the simple reason that there are astronomically more ways for its energy to be spread out and disordered than there are for it to be concentrated and ordered. It's just a numbers game. And that right there is the incredible power of this way of thinking. It connects the strange flickering of the quantum realm to the solid, tangible world we live in. By understanding the statistics of all those tiny, unseen parts, we can predict and explain the behavior of the whole system. And that unlocks the secrets behind literally everything, from something as simple as why water boils to something as complex as how the molecules of DNA hold together to create life itself. It truly is the bridge between worlds. And it makes you wonder, doesn't it? What other predictable things in our world are really just the result of a chaotic statistical dance we can't even see?